Hello students, welcome to EPG Pathshala. I am Dr. Nasir Iqbal from Department of Physics, University of Kashmir, Srinagar. Today we are going to talk on module Basic Optical Definitions under the paper of Astronomy and Astrophysics. After completing this module, the students will be able to answer the following things. What are the essential features of light? How light gathering phenomena is important for a good telescopic observations? In what context the focal length determines the magnification of an optical system? To distinguish between the apparent field and a true field? Do we classify telescopes on the basis of fast and slow ones? If yes, then how we can do it? Will the sky look always blue at a distance? How? How seeing conditions is important for good observations? What are the necessary conditions for a good telescope sight? We talk about the introduction of this module like light is a part of the electromagnetic spectrum which ranges from radio waves to gamma rays. Electromagnetic waves are fluctuations of electric and magnetic fields which transport energy from one point to another. Visible light is not actually different from the other parts of the electromagnetic spectrum, with the difference that the human eye can detect visible light very well. We can also discuss electromagnetic radiation as a stream of masses or as a stream of massless photons, each travelling with wavelength properties at the speed of light. A photon is the fundamental quantum of energy which can be transported, and it has been well accepted that light travels in discrete quanta, which basically reflects the originality of the quantum theory of light. Detection of light coming from various objects in the universe is very important for probing the universe around us. As and when the light emits from any celestial object, it interacts with the component of the matter present there, and as a result, the originality of this incident radiation will change. And by using the physics of the interaction of radiation with matter, the properties of matter can be described. The description of the module will be incomplete unless and until the student is not well versed with the basic details of a light, what exactly light is. Here we discuss the light, its origin, the light rays and the light waves. Light is an electromagnetic radiation usually detected by the human eye. Electromagnetic spectrum occurs over a wide range of spectrum corresponding to their energy, to their wavelength and to their frequency. The kind of this electromagnetic spectrum you can see here is shown in the given figure. In this given figure, in this spectrum, we talk about the gamma rays, the X-rays, the ultraviolet rays, the visible light, the infrared rays, the radio waves, the microwaves. So, in the spectrum of this electromagnetic The wavelengths visible to humans occupy a very narrow band from about 700 nanometers for red light to about 400 nanometers for violet light. The spectral regions adjacent to the visible band are often referred to as the light, also infrared at the one end and the ultraviolet at the other. The speed of light in a vacuum is a fundamental physical constant which is currently accepted value and is exactly about 299,792,458 meters per second, or roughly its value about 186,282 miles per second. Light is a sense of sight and is regarded as a primary tool for perceiving the world and communicating within it. We all know the sun emits the electromagnetic spectrum, as you have a different kind of radiations coming from the sun. So it drives global weather patterns and initiates the life-sustaining processes of photosynthesis. The interactions of matter and energy have helped many scientists to describe the shape and structure of the universe. Indeed, light provides a window on the universe from cosmological to atomic scales. The whole information about the universe reaches Earth in the form of electromagnetic radiation. The astronomers, while interpreting the received radiation on Earth coming from billions and trillions of stars, describe the chemical composition of stars and interstellar medium. The analyzing of the frequencies of light emitted and absorbed from atoms led to the development of quantum mechanics. However, atomic and molecular spectroscopy continued to be a primary tool for probing the structure of the matter. On the basis of the theory of classical electromagnetism, light is described as coupled electric and magnetic fields propagating through space as a traveling wave. However, this wave theory developed in the mid of 19th century is not a sufficient one to explain the properties of light at a very low intensities. Therefore, a quantum theory is needed to explain the characteristics of light and to explain the interactions of light with atoms and molecules. In its simple form, light consisting of a discrete packets of energy called photons, whose energy we describe by a very famous equation A is equal to h into nu, where h is a Planck's constant and nu is the frequency of the incident radiations. It's also said that neither a classical wave model nor a classical particle model correctly describes the definition of the light. So light has a dual nature that is revealed only in quantum mechanics. In the middle of 20th century, A more comprehensive theory of light, known as quantum electrodynamics, has been regarded by physicists as one of the appropriate theory for studying light as a whole. There are several laws which usually describe the properties or the characteristic features of this light. So every science student should be able to know the basic laws for studying the transmission of light, like the laws of reflection and the laws of refraction. How light reflects and refracts at smooth plane interface is described in the given figure. In this figure, it shows an ordinary kind of reflection at a plane surface, and its second part of the figure shows a refraction of light at two successive plane surfaces. At each instant, light is pictured simply in terms of straight lines, which we refer them as light rays. So while going through these two figures, we can see how the rays of light go for a reflection and a refraction at plane surfaces. After a study of how light reflects and refracts at plane surfaces, the procedure can be extended to smooth and curved surfaces, thereby having an interaction of light with mirrors and lenses, which are the basic elements in different optical systems. A light ray is like an imaginary line directed along the path that the light follows. It is helpful to think of a light ray as a narrow pencil beam or a narrow pencil of light, very much narrow and a well-defined kind of a laser beam. Now we talk about the light rays and the light waves. It's important to know the geometrical connection between the light rays and the light waves. Wave motion is visualized in terms of water waves as shown here in the figure. The successive high points, which we also refer them as crests, and the successive low points, which we also refer them as troughs, occur as a train of circular waves moving radially outwards from the bobbing cork. Each of the circular wave represents a kind of a front called as a wave front. A wave front is therefore defined as a locus of points that connects the identical wave displacements, that is, identical positions above or below the normal surface of that quiet pond. So you have here three kinds of pictures. In picture 1, we have the waves from a bobbing cork. In picture 2, we have the light rays and the wave fronts, giving an idea how the ray of light and how the wave front gets developed. In picture 3, we have the changing wave fronts and bending light rays. So showing here that how the light rays enter the lens after getting refraction, how they meet at the focus point. But once the refraction is there, you can see here we have a different fronts to be them called as the wave fronts. So in these figures we have the circular wave fronts as shown with radial lines drawn perpendicular to them along several directions. Each of the rays describes the motion of a restricted part of the wavefront along a particular direction. Hence, a ray is a line perpendicular to a series of successive wavefronts specifying the direction of energy flow in the wave. In the other part of this diagram, it shows plane wave fronts of light bent by a lens to a circular which can be spherical in 3 dimensions, and therefore we have wave fronts that converge onto a focal point. The same diagram shows that the light rays corresponding to these wave fronts bent by the lens to pass through the same focal point. This represents the connection between the actual waves and the rays used to represent them in the study of geometrical optics. We find it acceptable to represent the interaction of light waves with plane and spherical surfaces with mirrors and lenses in terms of light rays. Now we discuss here the reflection of light from optical surfaces. It's important to understand the kind of a situation that erupts when light is incident on an interface between two transparent optical media like air and glass, or between water and glass. So one of them is one medium, the another one is the other medium. While discussing this phenomena, there seem to be 4 possibilities that can happen to the incident light. Number 1, it can partly or totally reflected at the interface. Number 2, it can be scattered in random directions at the interface. Number 3, it can be partly transmitted via refraction at the interface and enter the second medium. Number 4, it can be partly absorbed in either medium. So, in the study of geometrical optics, smooth surfaces give rise to specular, which may be a regular, a geometric reflections, and ignore ragged, uneven surfaces give rise to diffuse, means irregular reflections. These things can be viewed from the given figure. In the first part, you have the smooth surface, and in the second part, you have the uneven surface. First part, in the smooth surfaces, you have a kind of a regular reflection, but the similar reflection cannot be viewed from the uneven surface. Light gathering and performance. The strongest perception in the minds of the people has been that the telescope automatically makes an object bigger and brings it closer and closer to us. We should remember that the first thing Galileo did in 1609 was to increase the magnification of the Dutch spy glasses. Because of the increase in magnification of the telescope, eyepieces enhance the angular, or simply the eyepieces enhance the angle under which an object is viewed, and thus there is an increase in its apparent angular diameter. Hence the image taken has a larger area of eyes, total field of view, while maintaining more or less its true appearance. Earlier observers have expressed the magnification as an increase in angular size. The telescope gathers more and more light. It gathers more and more light energy in the form of photons than the eye, making them available to form a brighter and more detailed image on any detector. The larger the lens or mirror, the larger, brighter and more bright and more distinct the image can be made. Therefore, it depends upon, to have a good quality image, it depends upon the diameter of the mirror or the lens. The energy gathering defines the true function of the telescope in terms of its brightness and resolution. Now we talk about the aperture and focal length. The diameter of the open area of an objective lens or primary mirror that receives incoming light represents its aperture. Every telescope primary optic focuses light as a specific distance away from its optical center. This distance is called as a focal length. For a lens objective, the central point is based on arranged optical powers of its component lens. For a surface, the focal length determines the magnification of a system. The focal ratio is basically defined as a ratio between any optical system whose focal length and aperture can be well viewed. For a human eye, the focal ratio can be very well calculated. The other parts of these properties of this light and light waves are discussed in terms of the field. It's important to discuss the basic idea of this field. Two types of field are taken into consideration in the telescopic view of observations. They are the true field and the apparent field. The apparent field of the eyepiece expresses the angle of view subtended by the circular view within its field and is independent of the telescope. True field, on the other hand, represents the angular measure of the image from the portion of 360 degrees circle. It has been found that binoculars have true fields between 4 degree to 6 degree only. True fields are usually calculated by the ratio between the apparent field of the eyepiece used and the magnification quantity. Standard eyepieces have about apparent fields between 40 to 65 degrees. For any telescope, the correct figure drawn and the focal length of its main optical elements are the primary physical descriptors of the telescope. This is true for all kinds of mirrors and lenses used in a telescope. If these two things are up to the mark, then be sure that the performance of telescope will be good. Now we discuss what are the fast and the slow telescopes. This fast and slow telescopes is actually a technical term that we use or describe in the functioning of these telescopes. We call a telescope with a low f by s ratio number as the fast one and a telescope with a large f to s ratio number as a slow one. It has been seen that a low f ratio photographic lens exposes film more quickly as compared to the large f by ratio. Telescope makers have found that when the ratio like f by ratio is about 12 or higher, telescopes are slower. moderate telescopes have f/8 and the fast one telescopes have been found with an approximate values lying between f/4 to f/5. One more important term that we discuss in functioning of the telescope is the magnification. Magnification, we define it as the ratio between the focal length of the optical system and that of the eyepiece. So, magnification is focal length of objective to the focal length of the eyepiece. High magnification is achieved by using eyepieces of very short focal lengths. Under perfect conditions of the telescope, the aperture of the objective and the quality of the optics define the useful magnification of the object. It may be noted that, keeping in view that image can be magnified beyond some threshold value, it is not possible at all. We also talk about the sky, which is blue and which has to be clear for good observations. Therefore, we have to remind what we mean by a clear blue sky. That depends upon the color, the brightness and the polarization. These are the three important parameters that one should know while talking about the sky. Now, but exactly we talk about the color, what we mean by the color. The sky, as we know, that contains all colors. Near the horizon, it is almost white, but it may be tinted one of several colors due to the reflection from the ground. So, what about the brightness? It is the faintest at the zenith and rapidly brightness near the horizon. The sky is also darker at higher elevations. And what about the polarization? Light from the sky is polarized. We all know it, which varies between about to 85% at 900 wavelength from the sun to 0 at other place. When you talk about the sun, so we have to talk about the sunlight. This sunlight consists of light of every wavelength and polarization planes. The unpolarized light is very close to a perfect white. As it reaches the earth, it begins filtering through the atmosphere. As we know that it is the Rayleigh theory of scattering that says that the probability that a single photon of sunlight will be scattered from its original direction by iron molecules, which is not directly but inversely proportional to the fourth power of the wavelength. Therefore, from this very simple mathematical significance, we can feel that the shorter the wavelength or below the light is, the greater it enhances or being scattered. Thus, when we look in any part of the sky except directly towards the sun, we mostly see a blue portion of scattered sunlight than a red one. So that is why the sky looks like blue. So this causes the sky to appear as the blue one. The brightness of the sky is determined by the number of molecules in the line of sight. More there molecules mean a brighter sky. From a high flying jet, the sky is darker than it is seen actually from the ground. This is because there are very few iron molecules in the line of sight. In space or on the moon, there are no molecules and therefore no scattered light is there in the brighter sky. There the sky looks like black. One more important term that we describe in the functioning of telescope is the seeing condition, or generally referred as seeing conditions. Astronomers describe the sky atmospheric conditions by using a technical term, seeing. Atmosphere is never smooth but continues to be always in a state of continual motion, which results due to changing temperatures, air currents, weather fronts, and dust particles. These factors cause the star's image to twinkle. Twinkling of stars considerably have poor seeing conditions. If these factors are very less, we see that we have good seeing conditions. Poor seeing is most noticeable when observing planets and the moon, whereas deep sky objects such as a nebulae and galaxies are less affected by the conditions of poor seeing. On deep sky objects, the most important factor is the transparency of the atmosphere, which is a measure of how dark the sky is one of a given night, determined by clouds or by dust, a haze, and a pollution. Sea conditions and transparency vary widely from site to site, means from place to place, from season to season, and from night to night. Seeing is used to indicate the quality of the observing conditions at the time of observation. It is the first point of the observer to evaluate the effects of atmosphere, to evaluate the effects of turbulence and impurities on the results of the observing. So students, let us see what we are going to learn from this module. The first one that we can learn, we can study, is the origin of light and its spectrum. The second one, we can talk about various optical laws like the law of reflection, the law of refraction, and how the reflection of light takes place from various optical surfaces. The other one that we can learn is what we mean by the phenomena of light gathering of an optical system. The other one we can learn is that how an optical system has to act as a good performer, or how any optical system has a good performance. The other one, what are the various parameters which are must to have a good performance of an optical system. And we can learn about what we mean by the aperture, what we mean by the focus, what we mean by the focal length, and how they are intercorrelated with each other. And we can talk about what we mean by the field of an optical system, its specific relevance with respect to certain observations. We can talk about what are the various factors which classify the telescopes on the basis of its fast and slow ones. And one more important thing that we can learn is that what we know about the magnification of an optical system. Therefore, on the basis of this magnification, we can even classify various telescopes. And The other important thing that we can learn is that what sky exactly it is in respect of its color, and if we want to have a good telescopic observations, which conditions we should keep into consideration. Thank you.